Imagine discovering that the universe is not what everyone believes it to be. Imagine proving it, and then being ordered to deny it. In a small stone farmhouse outside Florence, an old man sits in near darkness. He is 70 years old. His hands tremble. His eyesight has faded into little more than shadows and blurred light. Beyond the walls, the Tuscan hills roll quietly beneath a muted sky. Olive trees whisper in the night wind. And somewhere above the clouds, unseen but unwavering, Jupiter continues its slow orbit around the sun. Galileo Galilei cannot see it anymore, but he knows it is there. Decades earlier, with a small hand-ground lens lifted toward the Italian sky, he watched tiny points of light circle that distant planet. Moons, worlds revolving around another world. In that quiet observation, 2,000 years of certainty began to crack. The Earth was no longer the unquestioned center of creation. The heavens were not perfect and unchanging. The universe was larger, stranger, and far more beautiful than anyone had dared to imagine. For this he was condemned. The church placed him under house arrest. He was forbidden to publish, forbidden to travel, forbidden to teach what he had measured with his own hands, asked to declare false what he knew with absolute clarity to be true. And yet, in that farmhouse, nearly blind and physically confined, Galileo continues to write. He continues to calculate. He continues to think. If you find yourself drawn to these quiet journeys into the past, stories where history unfolds slowly, thoughtfully, and without hurry, consider subscribing to the channel. It truly helps these long, immersive histories continue to exist, and you will always be welcome here. Now make yourself comfortable. Let the noise of the day begin to fade. This is the story of Galileo Galilei, the man who reshaped humanity's understanding of the cosmos, and who stood, aging and alone, beneath the silent turning of the stars. To understand what Galileo broke, you first have to understand how completely solid the thing was that he broke it from. Not just solid as in widely believed, but solid as in foundational to everything. Theology, philosophy, medicine, navigation, agriculture, poetry, and the very idea of what it meant to be a human being in a cosmos designed by God. The structure of the universe, as understood in 1564 when Galileo was born, had been in place in essentially the same form for nearly 2,000 years. And it was, by any reasonable standard, a magnificent and internally consistent vision. It began with Aristotle. Born in 384 BCE in Macedonia, Aristotle was the student of Plato and the tutor of Alexander the Great, and he was one of the most systematically brilliant minds in the history of human thought. In nearly every field he touched, he produced frameworks of understanding so comprehensive and so intellectually satisfying that they dominated Western thinking for centuries. In the realm of natural philosophy, what we would now call physics, he proposed a picture of the cosmos that was elegant, hierarchical, and deeply purposeful. At the very center of Aristotle's universe sat the Earth, unmoving, heavy, the natural resting place of the earthly elements. Surrounding it in perfect concentric spheres were the Moon, Mercury, Venus, the Sun, Mars, Jupiter, and Saturn. Beyond all of these, at the outer rim of everything, were the fixed stars, unchanging and eternal. Each of these spheres was made from a substance Aristotle called the fifth element, or quintessence. Unlike the four terrestrial elements of earth, water, fire, and air, quintessence was incorruptible and eternal. It could not decay. It could not be imperfect. The heavens, by definition, were perfect. They were unchanging. They moved only in circles because the circle was the most perfect of all geometric forms, complete in itself, without beginning or end. This architecture had an enormous emotional and spiritual appeal. It placed the Earth at the center, yes, but it also placed the Earth at the bottom, the lowest and heaviest point, while the heavens ascended in rings of increasing perfection toward the primomobile, the outermost sphere, and beyond it, the unmoved mover, which Aristotle identified as the ultimate cause of all motion. When Christianity later absorbed this cosmology, it was not difficult to identify the unmoved mover with God. The perfect and unchanging heavens above, the imperfect and changeable earth below. This was not just a picture of the sky, it was a moral map of reality. Heaven was literally above you. Aristotle's physics came with a cosmology attached. On Earth, he said, objects moved in accordance with their elemental composition. Heavy things were primarily made of earth and water, and their natural tendency was to move downward, toward the center of the universe. Light things were primarily fire and air, and they naturally rose. The speed at which an object fell was proportional to its weight. A stone twice as heavy would fall twice as fast. A stone 10 times heavier would reach the ground 10 times sooner. This was not merely a theory. It was, to most people who observed the world casually, confirmed by direct experience. Drop a leaf and a rock from the same height, and the rock clearly falls faster. Aristotle seemed to be simply describing what was already obvious. Then came Ptolemy. Claudius Ptolemy was a Greek astronomer and geographer who lived in Alexandria, Egypt, in the 2nd century of the Common Era. He took Aristotle's cosmology and clothed it in the most precise and sophisticated mathematical framework the ancient world had ever produced. His great work, the Almagest, was a systematic mathematical treatment of the motions of the sun, moon, and planets. Ptolemy's achievement was that his mathematical model could actually predict where the planets would be in the sky with remarkable accuracy. The model was used by navigators to chart their courses at sea, by farmers to predict the seasons, by physicians who believed that celestial configurations influenced health and disease, and by the Church itself to calculate the dates of Easter and other holy days. The system had one complication, which Ptolemy addressed with considerable mathematical ingenuity. Planets, when observed over months and years, do not simply move steadily in one direction across the sky. They occasionally appear to slow down, stop, and then move briefly backwards before resuming their forward motion. This retrograde motion was deeply puzzling to any model that had everything simply circling the Earth at uniform speed. Ptolemy's solution was to introduce epicycles, small circles upon which the planets moved, while the centers of those small circles themselves moved in larger circles around the Earth. The result was a complex but workable mechanism that, with sufficient adjustment of the sizes and speeds of the various circles, could match observed planetary positions to a degree that satisfied astronomers for 14 centuries. By the time Galileo was born in 1564, the Ptolemaic system had been the reigning cosmological framework for more than a millennium. It had been sanctioned by the Catholic Church, integrated into the theology of Thomas Aquinas in the 13th century, taught in every university in Europe, and treated in most intellectual circles as not merely a working model but as an established description of physical reality. The Earth was at the center. The sun and planets orbited around it. The stars were fixed in an outer sphere. The heavens were perfect and unchanging. There had been, it must be said, a beginning of doubt. In 1543, the same year Copernicus died, a book arrived that planted the seeds of the revolution that would eventually shake this entire edifice. Nicholas Copernicus was a Polish Catholic canon, a careful and deeply learned man who had spent decades working on a new model of the solar system. His book, De Revolutionibus Orbium Coelestium, on the revolutions of the heavenly spheres, proposed something radical: that the sun, not the Earth, sat at the center of the planetary system, and that the Earth was one of several planets orbiting around it. In this model, the Earth rotated on its own axis once a day, producing the apparent rotation of the sky, and it orbited the sun once a year, producing the apparent motion of the sun through the constellations. Copernicus made this proposal with characteristic caution. An earlier preface added by a Lutheran theologian, without Copernicus's permission, presented the heliocentric system as merely a mathematical convenience for computation rather than a description of physical reality. Whether this preface softened the book's initial reception is debated, but for the first decades after its publication, the Copernican system was read primarily by technical astronomers and treated more as a computational tool than as a challenge to cosmological orthodoxy. The Church made no immediate ruling against it. Many mathematicians found it useful, but very few people in those early decades were willing to stand up and say, "This is not a convenient fiction. This is actually how the universe is arranged." Into this world, balanced on the cusp between the old cosmology and the new, the first of 6 children was born to a musician and his wife in the city of Pisa on the 15th of February, 1564. His name was Galileo Galilei, and he would be the one to tip the balance. The Galilei family was a family of modest nobility and considerable intellectual vivacity. They were Florentine in origin, which was something they were proud of, even though Galileo was born in Pisa, where his father had temporarily settled to pursue his musical career. The family name carried a trace of old Florentine respectability, but it did not carry much money. This tension between social aspiration and financial precariousness would haunt Galileo throughout his early life and motivate some of the most important decisions he ever made. His father, Vincenzo Galilei, was a genuinely remarkable figure. A professional lutenist and composer of some distinction, he had studied music theory and become one of the more intellectually adventurous musical thinkers of the Italian Renaissance. He was a member of the Camerata de' Bardi, a Florentine intellectual circle that was at that very moment attempting to revive the dramatic music of ancient Greece, an endeavor that would eventually lead, indirectly, to the invention of opera. More germane to Galileo's intellectual formation, however, was Vincenzo's approach to questions of musical theory. He believed that the abstract rules of music handed down from ancient authorities, particularly the ancient Greek theorist Pythagoras and his later interpreters, needed to be tested against actual physical experiment. He conducted experiments on strings, changing their length, their tension, their material, and listening to the results. He weighed the evidence of his own ears against the authority of ancient texts. He trusted observation. This inclination, this belief that truth must be tested against the world rather than simply inherited from authorities, passed from father to son in ways that perhaps neither of them fully recognized at the time. Galileo's mother, Giulia Ammannati, was the daughter of a merchant family from Pescia, a small Tuscan town. She married Vincenzo in 1563, a year before Galileo was born. By all accounts, the marriage was often tense, the household sometimes stormy, the financial worries persistent. Vincenzo's musical career was not lucrative enough to keep the family comfortable, and as the oldest of 6 children, with 3 siblings surviving into adulthood, Galileo grew up in a household where money was always a concern. 3 of his younger siblings died in infancy, which was not unusual for the era but was nonetheless a shadow that touched the early years of the family. In 1572, when Galileo was 8 years old, the family moved to Florence. This was Vincenzo's home city, and the move was probably motivated by a combination of professional opportunity and family connection. But young Galileo did not immediately follow the family. He stayed behind in Pisa for 2 more years, living in the household of Muzio Tedaldi, a man connected to the Galilei family by marriage. This arrangement, a young child sent to live with a relative while the parents established themselves elsewhere, was not uncommon in Renaissance Italy, but it must have given Galileo an early lesson in independence and adaptability. When Galileo was 10, he joined his family in Florence and began his more formal education. He was tutored privately, first by a local teacher, and then by the monks of the Camaldolese monastery at Vallombrosa, situated on a beautiful forested hillside about 33 kilometers southeast of Florence. The Camaldolese were a contemplative order, and the monastery was a place of considerable learning. Here Galileo absorbed the standard humanist curriculum of the era: Latin, Greek, rhetoric, logic, and the beginnings of Aristotelian philosophy. He also, apparently, fell in love with the place. The quiet, the order, the intellectual seriousness, the rhythms of monastic life appealed to something deep in his nature. According to later accounts, he considered entering the order as a novice, taking the first steps toward becoming a monk. His father, who had very different plans for his eldest son, was not pleased. He removed Galileo from the monastery, using an eye condition as the official pretext, and brought him back to Florence to continue his studies in a more worldly setting. Vincenzo's plan for Galileo was straightforward and practical. The boy would study medicine. Medicine was one of the most lucrative of the learned professions. A successful physician could support a family handsomely. Vincenzo, struggling to keep his musical career financially viable while supporting a household and 2 younger daughters who would need dowries, needed his eldest son to generate income, and he needed it from a reliable source. In 1580, at the age of 16, Galileo enrolled at the University of Pisa as a student of medicine and philosophy. He settled into the house of his old guardian Muzio Tedaldi once more and began his studies. What happened next is one of those moments in history that has been surrounded with legend, but that also points towards something genuinely true about how Galileo's mind worked. At some point during his student years, probably around 1581, he was sitting in the Pisa Cathedral during a religious service. The cathedral was and remains a spectacular piece of medieval architecture, its interior filled with columns and arches and the play of light through high windows. Suspending from the ceiling was a large bronze lamp on a long chain, set swinging by some movement of air in the building. Galileo watched it oscillate back and forth, and he noticed something that struck him as strange. Whether the lamp was swinging in a wide arc or a narrow one, it seemed to take the same amount of time to complete each swing. He checked this against the only reliable timer he had available to him at that moment, his own pulse, placing his fingers on his wrist and counting the beats. The result was always the same: large swing, small swing, same duration. This observation, which his first biographer Vincenzo Viviani later described in detail, is the legendary beginning of Galileo's scientific career. Whether the specific anecdote of the cathedral lamp is accurate in all its details, or whether it is a narrative simplification of a more gradual discovery, historians debate. What is not in doubt is that Galileo in these early university years became fascinated with the behavior of pendulums, testing them with different lengths and different amplitudes of swing, and that he eventually established the principle of isochronism. The period of a pendulum, the time it takes to complete one full swing, depends on the length of the pendulum and not on how far it swings. This was the opposite of what everyday intuition suggested. It was a principle that would, decades later, lead to the invention of the pendulum clock. And it was the kind of discovery that came from watching carefully and measuring precisely, not from reading Aristotle. Galileo was not, to put it gently, a devoted student of medicine. The university curriculum required him to attend lectures on anatomy, pharmacology, and the ancient medical texts of Galen. He found these subjects dull. What captured his attention was mathematics. He was drawn to the lectures and the texts of Euclid and Archimedes. The elegance of geometric proof, the way mathematical reasoning could establish truths with absolute certainty, the beauty of the numerical relationships that describe the natural world. These things electrified him in a way that the memorization of Galenic prescriptions simply did not. The moment that crystallized his change of direction came through an almost accidental encounter. Astilio Ricci was a mathematics teacher attached to the Tuscan court and the Florentine Academy of Design, and he happened to be lecturing at Pisa during Galileo's student years. Galileo heard him speak, was immediately captivated, and began attending his lectures in secret, since mathematics was not on his official curriculum. Ricci became his first real mathematical mentor. Through Ricci, Galileo encountered Archimedes, the ancient Greek genius of mathematics and mechanics, and this encounter was transformative. Archimedes had understood the mathematics of levers, of centers of gravity, of hydrostatics. His work was precise, quantitative, testable. It was the kind of thinking Galileo found natural and exciting. By around 1585, Galileo had left the University of Pisa without completing his medical degree. He had no diploma, no official certification, and no clear professional path. His father was disappointed, though not entirely surprised. Galileo returned to Florence and began to make his way as an independent mathematical scholar, giving private lessons in mathematics and geometry to supplement the household income. It was a precarious existence, but it was his existence, and his mind was free to pursue the questions that truly interested him. In 1586 he wrote his first scientific work, a short treatise he called La Bilancetta, the Little Balance. It was an elegant piece of practical geometry applied to a real problem: how to determine the precise specific gravity of a metal or mineral sample using a scale that worked in both air and water, following the principle Archimedes had used to detect the adulteration of a golden crown. The work was not published but circulated in manuscript among the small community of Italian mathematicians, and it got Galileo noticed. He was clearly a young man of unusual mathematical gifts. 2 years later, in 1588, he was invited to lecture at the Florentine Academy, one of the most prestigious literary and intellectual societies in Italy, on the physical dimensions of Dante's Inferno as described in the Divine Comedy. Galileo applied mathematical analysis to Dante's vision of hell, calculating the size of its chambers, the height of its giants, the geometric implications of its architecture. The lectures were a success, combining technical brilliance with literary culture in a way that earned him admirers in exactly the circles he most needed to impress. And the impression was lasting. It brought him to the attention of Guidobaldo del Monte, a nobleman and accomplished mathematician who became a crucial patron, recommending him for the chair of mathematics at the University of Pisa. In 1589, 25 years old and still without a degree, Galileo Galilei became a professor of mathematics. The mathematics professorship at Pisa came with a salary that was, by the standards of the era, quite modest, 60 scudi per year, which was considerably less than the salaries of professors of medicine or law at the same institution. But it came with a platform, with students to teach and with colleagues to argue with, and arguing, as Galileo's contemporaries quickly discovered, was one of his great pleasures and one of his most formidable intellectual tools. From his first days as a professor at Pisa, Galileo was drawn back to the question that had been bothering him since his student years: the Aristotelian theory of motion. Aristotle had said that heavier objects fall faster than lighter ones. This was not a peripheral claim. It was central to Aristotle's entire theory of how elements behave in the sublunary realm. The speed of fall was a direct expression of the object's elemental composition, the amount of downward-seeking earth it contained. And it had the apparent virtue of matching everyday experience. A stone dropped alongside a feather falls faster, obviously. Aristotle seemed to be telling the truth, but Galileo was suspicious of the obvious. He began to think through the implications of Aristotle's claim with the rigorous logic of a mathematician, and he found a contradiction at its heart. The argument went something like this: take two objects, one heavy and one light. According to Aristotle, the heavy one falls faster and the light one falls slower. Now tie them together. By Aristotle's logic, the combined object is heavier than either one alone. and should therefore fall faster than either. But wait, the lighter one, being naturally slower, should also act as a kind of drag on the heavier one, slowing it down. So the combined object should fall both faster and slower than the heavy one alone. This is a logical contradiction. Aristotle's theory is internally inconsistent. This argument, which appears in a manuscript Galileo wrote at Pisa called De Motu on motion, was not entirely original to him. Versions of it had been anticipated by earlier thinkers. But Galileo worked it out with unusual clarity and rigor, and he understood its implications better than most. The contradiction showed that Aristotle's theory could not be right as stated. Something else was going on when objects fell. De Motu was never published in Galileo's lifetime, and for good reason. It was a working document full of experiments and arguments that he later revised and improved as he discovered new things. But it was an important intellectual step, because embedded in it was something that would become central to Galileo's entire method. The idea that you could test theories about falling bodies by using an inclined plane to slow the motion down to a measurable rate. A ball rolling down a gently sloped surface was essentially experiencing the same forces as a freely falling ball, but spread out over a longer time at a more tractable geometry. This insight was not immediately acted upon at Pisa, but it planted a seed that would bear fruit a decade later in Padua. What Galileo did act on at Pisa, according to his biographer Vincenzo Viviani, was the dramatic and now legendary demonstration at the Leaning Tower. The story, as Viviani tells it, is this: Galileo climbed to the top of the famous tilted campanile, the bell tower that has been listing gently southward since construction began in the 12th century, and from its height he dropped 2 cannonballs of different weights simultaneously. Both balls struck the ground at virtually the same moment. The watching crowd of professors and students, assembled to witness what everyone expected to be an obvious demonstration of Aristotelian physics, instead witnessed its refutation. Historians have scrutinized the story with considerable care. The balance of current scholarly opinion is that the specific public demonstration described by Viviani probably did not happen exactly as narrated, or at least cannot be corroborated by any contemporary source. A Dutch experimenter named Simons Devine had actually performed a similar experiment in Delft in 1586. Dropping lead balls of different masses from the tower of the Nieuwe Kerk and recording that they hit the wooden platform below at the same time. It is entirely possible that Galileo conducted similar informal experiments at Pisa without the theatrical public staging Viviani describes. What is clear is that Galileo was thinking deeply about the problem of falling bodies at this time and was testing Aristotle's predictions against observation, and that his observations were leading him toward conclusions that contradicted Aristotle. His professorial years at Pisa were productive but not happy. He was contentious by nature, prone to pointed criticism of the conventional wisdom, and not particularly concerned with softening his arguments for the comfort of colleagues who disagreed with him. He made enemies. He was, in particular, dismissive of Aristotle's followers who argued from textual authority rather than from observation, and they knew it. His salary, already low, was reportedly not increased when he came up for renewal, which may reflect how well regarded he was by the university establishment. He also suffered his first great personal loss in this period. His father Vincenzo Galilei died in 1591, leaving Galileo as the head of the family and responsible for the financial welfare of his mother and siblings. His youngest brother Michelangelo was an aspiring musician who would, over the coming years, cost Galileo considerable sums in borrowed money and unfulfilled financial obligations. His 2 sisters needed dowries which were expensive. The financial pressures that had haunted his childhood now became his own direct responsibility. It was in this context that the offer from Padua arrived like a lifeline. In 1592, at the age of 28, Galileo accepted the chair of mathematics at the University of Padua, in the Venetian Republic. His salary there was 180 scudi per year, 3 times what he had been earning at Pisa. The University of Padua was one of the oldest and most distinguished universities in Europe, founded in 1222, and it attracted students and scholars from all over the continent. The Venetian Republic, which governed Padua, was notable in the Italy of that era for its relative intellectual openness. Venice was a trading city, pragmatic and cosmopolitan, less deferential to papal authority than the Florentine or Roman states, and the university reflected this culture of greater latitude. Ideas could be discussed at Padua with a freedom that was harder to find elsewhere. On December 7, 1592, Galileo delivered his inaugural lecture. He was assigned to teach Euclid's geometry and standard, that is to say geocentric, astronomy to medical students, who needed some astronomical knowledge for the practical reason that astrology was considered a legitimate tool in medical practice. He also taught Aristotelian physics and mechanics. The irony of this was not lost on him. A man whose deepest intellectual convictions were leading him away from Aristotle was required to teach Aristotelian cosmology to earn his living. He did it competently, but he taught it as Aristotle's system, not as physical truth. Students who came to his lectures later recalled that he would sometimes point out the weaknesses in Ptolemaic astronomy while still presenting it as the official curriculum demanded. Outside the classroom, Galileo was doing very different work. He returned to the problem of motion with the full concentration that his relative financial stability now permitted. The great project of the Padua years, the one that would eventually become the scientific centerpiece of his final masterwork, was the inclined plane experiments. These experiments were brilliant in their simplicity and painstaking in their execution. The setup was this. A long, straight groove or channel was cut into a plank of wood and lined with parchment, giving a smooth, consistent surface. The plank was elevated at one end to create an incline, and a bronze ball was rolled down the groove from various heights. Galileo measured the distance the ball traveled during each time interval, using a water clock to track the time. A large container of water with a narrow tube at the bottom. The water collected during each measurement and then weighed on a precise scale to compare the durations. The experiments were performed hundreds of times, at different angles of inclination and with different heights of release. The results were consistent and clear. The distance a ball rolled during successive equal time intervals followed a precise numerical pattern. If the distances in the first, second, third, and fourth time intervals were measured, they stood in the ratio 1 to 3 to 5 to 7, the sequence of odd numbers. The total distance traveled from the start grew as the square of the time elapsed. Roll for 1 unit of time and the ball covers 1 unit of distance. Roll for 2 units of time and it covers 4 units of distance. Roll for 3 units of time and it covers 9 units. The distance always grows as the square of the time. This is what physicists now call uniformly accelerated motion, or motion with constant acceleration. And the beautiful numerical simplicity of the result? The square of the time law held regardless of the weight of the ball or the material it was made from. A heavier ball rolled down the same incline at exactly the same speed as a lighter one. Aristotle had been completely, demonstrably, and repeatedly wrong. It is worth pausing here to appreciate how philosophically radical this result was. For nearly 2,000 years, educated people have believed that heavier objects fell faster, because the greatest philosopher who had ever lived said so and because casual observation seemed to confirm it. And yet the actual measurement, conducted with patience and precision and repeated hundreds of times under different conditions, gave a completely different answer. The world was not behaving the way the authorities said it behaved. Galileo's response was not to question his instruments or to defer to Aristotle and conclude that something must be wrong with the experiment. His response was to trust the measurement, to record the result, to follow it wherever it led, even when it contradicted 2,000 years of intellectual tradition. This was the scientific revolution in miniature, the conviction that what we observe takes precedence over what we have been told, and that nature, questioned carefully with instruments and numbers, will always answer honestly. No authority, however ancient, however brilliant, however deeply embedded in theology and philosophy, can override a careful measurement. This conviction was not universally accepted in Galileo's day. It is, in fact, still resisted in various forms today. Galileo held it more consistently and more courageously than almost anyone of his era, and that is why his name is attached not just to moons and telescopes but to a way of thinking. There was another implication that Galileo grasped and that the ancient authorities had entirely missed. The rate of acceleration due to gravity was the same for all objects, regardless of their weight or composition. The reason a leaf falls more slowly than a stone is not because the stone has more downward-seeking tendency. It is because the leaf is more strongly affected by air resistance relative to its weight. In a vacuum, stone and feather would fall together. This was not something Galileo could demonstrate directly, since the technology to create a practical vacuum did not exist in his time. But he could reason toward it logically from the patterns he observed, and the reasoning was airtight. The inclined plane work was the foundation. But Galileo was also thinking about projectile motion during these years. If an object is launched horizontally, it has 2 motions simultaneously: the horizontal motion imparted by the launch and the vertical acceleration due to gravity. Galileo worked out that these 2 motions are independent of each other. The horizontal motion continues at a constant rate, unchanged by gravity, while the vertical motion accelerates downward at a uniform rate. The combination of these 2 independent motions produces a curved path. and Galileo was able to show mathematically that this curve is a parabola. This was a remarkable unification, connecting the abstract geometry of conic sections to the actual trajectories of stones and cannonballs through the air. While all of this physics was being worked out in the evenings and on quiet days, Galileo was also building a remarkably rich and multifaceted life. He was a popular teacher. His lectures attracted large numbers of students, and he supplemented his income by taking private students who paid for additional instruction. He ran a small workshop in his home, where artisans made and sold copies of a calculating instrument he designed, essentially a sector or proportional compass useful for military and engineering calculations, along with a manual explaining its use. He consulted for practical engineering projects. He visited the Arsenal of Venice's enormous shipyard and military manufacturing complex, where he studied how ships were constructed and how loading and leverage affected their behavior. These visits fed into his thinking about the strength of materials, a subject he would eventually treat in the first half of Two New Sciences. And then there was Marina Gamba. At some point during the Padua years, probably in the late 1590s, Galileo began a relationship with a Venetian woman named Marina di Andrea Gamba. She was from a modest family, and the relationship was never formalized by marriage. The reasons for this are not entirely clear, but they were probably related to the social dynamics of the era. For a university professor of Galileo's social pretensions and financial obligations, formally marrying a woman without social standing or property could have been professionally and socially awkward. Whatever the calculation, the relationship was genuine and enduring. Marina came to live with Galileo in Padua. Together they had 3 children: Virginia, born in 1600, Livia, born in 1601, and Vincenzo, born in 1606. The children's birth records did not list Galileo as the father. They were listed as children of Marina Gamba alone. This was a social and legal convention that reflected his unwillingness or inability to formally claim them at the time, though later in life he did acknowledge them all and worked to provide for them. The daughters, born into legal irregularity and unable to marry above their station with ease, were eventually placed in the convent of St. Matthew in Arcetri, near Florence, when they were still children. The older one, Virginia, took the name Sister Maria Celeste on entering religious life. The younger, Livia, became Sister Archangela. Virginia, Sua Maria Celeste, would become one of the most important people in Galileo's later life. His confidant, his emotional anchor, the person who managed much of his domestic correspondence and provided him with warmth and understanding during the most difficult years of his life. Their letters, preserved and published centuries later, give us our most intimate window into Galileo as a person rather than as a symbol. When Galileo left Padua in 1610 for Florence, Marina did not go with him. Their relationship ended, though not acrimoniously. Vincenzo, the son, eventually followed his father. The 2 daughters remained in the convent for the rest of their lives. The Padua years, with all their intellectual productivity and personal complexity, came to an end because of something that happened in the spring of 1609 that changed the course of everything. The story of how news of the telescope reached Galileo in the spring of 1609 is one of those moments where the transmission of an idea across geographical distance produces consequences that no one at the time could have anticipated. In the Netherlands, in the city of Middelburg, a spectacle maker named Hans Lippershey had in 1608 applied to the States General of the Netherlands for a patent on a device he called a looker, an instrument consisting of 2 lenses mounted in a tube that made distant objects appear closer. The application was ultimately denied on the grounds that the device was too simple to be kept secret, but the word had spread quickly. Within weeks, other Dutch craftsmen were making similar instruments, and by early 1609 the device, variously called a spyglass or perspective glass, had reached Paris and was making its way around Europe. Galileo, in Padua, heard of the Dutch invention through his friend Paolo Serpi, a Venetian theologian and statesman who had excellent connections throughout Europe. The news arrived in May or June of 1609. Galileo's response to this information was characteristic. Rather than seeking to obtain a Dutch instrument, he sat down and thought through how it must work. He had enough knowledge of optics to reason out the principle. 2 lenses, one convex and one concave, positioned at the right distance from each other, could form an image that appeared magnified. He went to a spectacle maker, bought some lenses, tried various combinations until he found the right arrangement, and built himself a working telescope within a matter of weeks. His first telescope had a magnification of about 3 diameters, meaning it made objects appear 3 times larger in linear dimension, or about 9 times larger in area. Others had built similar instruments by this point. What set Galileo apart was what he did next. He immediately began improving it. He taught himself the art of lens grinding, using techniques and materials that allowed him to produce lenses of higher quality and more precise curvature than the commercially available spectacle lenses. Within weeks he had built a telescope of 8 or 9 diameters. By late summer he was working on one that magnified 20 times, and by November of 1609 he had an instrument that reached approximately 30 times magnification. On August 25, 1609, Galileo demonstrated one of his telescopes to the Venetian Senate, the governing body of the Republic of Venice. The demonstration took place from an elevated location, probably a tower or high building near the Piazza San Marco, and the senators took turns looking through the instrument at the Venetian lagoon and the sea beyond. Through the telescope, ships that were invisible to the naked eye became clearly visible. Ships that the naked eye could barely distinguish became sharp and legible. The military and commercial value was immediately obvious. An enemy fleet, a trading vessel, a storm on the horizon, all could be detected hours before they would otherwise become visible. The senators were captivated. They rewarded Galileo with a lifetime appointment at the university and a doubling of his salary. They also, he would later discover with some irritation, immediately realized that similar instruments were being sold in shops throughout Venice for a fraction of what Galileo had implied was a unique invention, and they never gave him another salary increase. But that was a minor annoyance compared to what was about to happen, because Galileo had already done something more important than show the senators ships on the horizon. He had turned his telescope toward the sky. The precise chronology of Galileo's first telescopic observations of the heavens is slightly uncertain, but the broad outlines are clear. Sometime in late November or early December of 1609, probably around the end of November, Galileo directed one of his high-powered telescopes at the moon and began to look. The moon was one of the standard objects of ancient astronomy, but it had never been examined at anything like this level of magnification. What Galileo saw when he looked was so completely at odds with what he had been taught that he spent several nights sketching and resketching the image to make sure his eyes were not deceiving him. The moon's surface was not smooth. It was not the perfect, unblemished sphere of quintessence that Aristotle had described and the entire edifice of medieval cosmology had taken for granted. The moon was rough, irregular, mountainous. Its surface was covered with bright areas and dark areas, with circular depressions that looked disturbingly like bowls or craters, with ranges of what could only be mountains casting long shadows across the lowlands. Along the terminator, the curving line that separated the sunlit part of the moon from the shadow, Galileo could see isolated points of brightness separated from the main illuminated area, exactly as you would see the sunlit peaks of a mountain range rising above a still-shadowed valley in the early morning. Galileo had trained as a painter and musician, and he understood the visual language of light and shadow, what Italian Renaissance artists called chiaroscuro, as well as anyone alive. He used this training to read the lunar surface the way a surveyor reads a landscape. He could estimate the heights of the lunar mountains by measuring how far the illuminated peaks were from the nearest portion of the terminator and calculating the angle from which the sunlight was striking. He worked out that some of the mountains on the moon were at least 4 miles, roughly 6.5 kilometers, in height comparable to the highest mountains on Earth. The moon was not a perfect sphere. It was a world, a physical world with geography. This single observation was already revolutionary enough to overturn the theoretical distinction between the perfect heavens and the imperfect Earth. But Galileo kept looking. He turned his telescope to the stars and discovered that they were far more numerous than the naked eye could perceive. In the constellation of Orion, where the naked eye saw 9 stars in the belt and soared together, the telescope revealed more than 80. In the Pleiades, where 6 stars were visible without a telescope, the telescope showed 35. The Milky Way, which had long been a subject of speculation, was resolved by the telescope into an enormous mass of individual stars, too faint and too close together to be distinguished by the naked eye alone, but unmistakably present when magnified. The universe was vastly larger and more populous than it appeared. And then came the night of January 7, 1610. On the night of January 7, 1610, Galileo set up his telescope on the balcony of his house in Padua and turned it toward Jupiter. The planet was bright in the winter sky, one of the most prominent objects visible. Through the eyepiece, Galileo saw something that immediately caught his attention. 3 small, faint points of light arranged in a straight line very close to Jupiter. 2 were to the east of the planet and 1 to the west, all lying almost exactly on the line of the ecliptic, the band of sky along which the sun, moon, and planets travel. He noted their positions carefully in his observation notebook and assumed, initially, that they were simply 3 fixed stars he had not noticed before. But on January 8, when he looked again, they had moved. All three were now to the west of Jupiter. Fixed stars do not move relative to each other or to a planet on consecutive nights. Galileo was puzzled. He recorded the new positions and waited. On January 10th, bad weather prevented observation. On January 11th, he returned to his telescope and found that only 2 of the 3 points were visible, and their positions had changed yet again. On January 12th, all 3 were back and their arrangement had shifted again. By January 13th, a 4th small star had appeared. The evidence was unmistakable. These were not fixed stars at all. They were objects moving around Jupiter. They were, in short, moons. Jupiter had 4 moons orbiting it, just as our moon orbits the Earth. Galileo confirmed this over the following weeks, eventually working out that all 4 moved in regular, predictable orbits around the planet, with the ones closer to Jupiter completing their orbits faster than the ones further away, just as the inner planets orbit the Sun faster than the outer ones. The cosmological implications of this discovery were profound and immediate. In the Ptolemaic Aristotelian system, everything in the heavens revolved around the Earth. The Earth was the center not just geometrically but physically and philosophically. One of the standard objections to the Copernican system was this: if the Earth moves around the Sun, what happens to the Moon? Wouldn't the Moon get left behind or fly off into space as the Earth moved away from it? The existence of Jupiter's moons provided a direct and visible answer to this objection. Here was a planet, quite obviously not at the center of the universe, that had 4 moons orbiting it without any apparent difficulty. If Jupiter could carry its moons along as it moved through space, then there was no reason why the Earth could not do the same with our moon. The geocentric model had suffered a wound it could not recover from. Galileo worked quickly. He had known from the moment he first saw those strange points of light near Jupiter that he had something extraordinary on his hands, something that needed to be published and published fast, before someone else made the same discovery and got the priority claim. He wrote up his observations in a short treatise, drafted in Latin so that it could be read by scholars throughout Europe, and had it printed in Venice. The book was published on March 13, 1610. Its title was Sidereus Nuncius, the Starry Messenger, or perhaps more accurately, the Message from the Stars. It was approximately 60 pages long, illustrated with Galileo's own careful engravings of the moon and his observation diagrams of Jupiter and its moons. 550 copies were printed. They sold almost immediately. The Sidereus Nuncius reported 4 major discoveries. First, the moon's mountainous and irregular surface. Second, the vast number of previously invisible stars visible through the telescope. Third, the resolution of the Milky Way into individual stars. And fourth, the 4 moons of Jupiter, which Galileo named the Medicean stars in honor of the Medici ruling family of his native Tuscany. This last naming was not purely scientific. It was a piece of deliberate and carefully calculated patronage politics. Galileo was angling for a position in Florence, and naming the 4 new moons after the 4 brothers of the Medici family was a gift that no ambitious nobleman could easily ignore. The book landed like a stone in still water, sending ripples in every direction. In Florence, Grand Duke Cosimo II de' Medici, the former student whom Galileo had tutored in mathematics during his Padua years, was delighted. In Rome, the Jesuits at the Collegio Romano, the most intellectually sophisticated Catholic institution in Europe, were galvanized into action, pointing their own telescopes at Jupiter to check Galileo's claims. In Prague, Johannes Kepler, the greatest theoretical astronomer of the age, received a copy and wrote back with enthusiasm and admiration. In England, the philosopher and statesman Francis Bacon read it with fascination. In Germany, skeptics questioned whether the telescope was a reliable instrument for celestial observation or merely an engine of optical illusion. Within months, the confirming observations came from the Jesuit astronomers. Christoph Clavius, the senior mathematical astronomer at the Collegio Romano, and one of the most respected scientists in Europe, confirmed that the moons of Jupiter were real. They moved around the planet just as Galileo described. The Collegio Romano verified all of Galileo's major claims: the lunar mountains, the stellar multitudes, the Medicean stars. Clavius was not ready to abandon Ptolemy, and he remained skeptical about some of the theoretical implications, but the observations themselves were confirmed. Galileo did not wait around for the confirmations. He had already engineered his return to Florence. In June 1610, just 3 months after the publication of the Sidereus Nuncius, he resigned his professorship at Padua, an institution where he had spent 18 fruitful years and where he later said he had been happier than anywhere else in his life, and accepted the position of chief mathematician and philosopher to the Grand Duke of Tuscany, headquartered in Florence. The title was important, not just mathematician but philosopher. This was a claim to intellectual authority over questions of natural philosophy, the study of the physical world, which was precisely the territory he intended to occupy. Galileo's celestial observations did not stop with the Sidereus Nuncius. In the autumn of 1610 he turned his telescope to Venus and made a discovery that was in some ways even more significant than the moons of Jupiter. He observed that Venus showed phases just as the moon does. Sometimes it appeared as a thin crescent, sometimes as a half-circle, sometimes nearly full. In the Ptolemaic system, where Venus orbited between the Earth and the Sun in a relatively tight circle, Venus should always appear in roughly the same illuminated configuration, since it was always between us and the Sun. It could never appear fully illuminated from our perspective, because we would always be seeing its night side or a partial phase. The fact that Venus showed a complete range of phases from crescent to nearly full could only be explained if Venus was orbiting the Sun at a distance greater than our own, so that sometimes it was on the far side of the Sun from us and we could see its fully sunlit face. This was direct visual evidence that Venus revolved around the Sun. The Ptolemaic system could not accommodate it. The reaction to the Sidereus Nuncius was not uniformly enthusiastic. Among the scientific skeptics, a strong current of doubt ran through the question of whether the telescope itself could be trusted when pointed at the sky. On Earth, the instrument clearly worked. You could look through it at a tower on the horizon and verify that what you saw matched the tower's actual appearance. But the heavens were different. Many scholars argued that the lens might produce optical artifacts, false images, ghostly appearances that did not correspond to real objects. The instruments of that era were indeed imperfect. The glass was not always uniform in quality, and lenses could introduce distortions. How could Galileo be certain that the four little stars near Jupiter were not aberrations introduced by the glass itself? Galileo addressed these objections with characteristic directness and with the only argument that actually matters in science. He invited skeptics to look for themselves. He sent telescopes to interested astronomers throughout Europe. He published detailed descriptions of how his instruments were made and used, and he challenged anyone who doubted his observations to replicate them. The crucial validation, as noted, came from the Jesuits at the Collegio Romano, and it came quickly. Within a year of the Sidereus Nuncius, the leading Jesuit astronomers had confirmed everything Galileo had reported. Christoph Clavius himself, the most respected mathematical astronomer in the Catholic world, admitted that he had seen the moons of Jupiter moving around that planet. Whatever doubts he had about the theoretical implications, the observations were real. Galileo also observed sunspots, the dark regions on the sun's surface that a telescope could just barely detect by projecting the solar image onto a screen in a darkened room. The existence of sunspots was itself a serious problem for the Aristotelian conception of perfect and unchanging heavens. The sun clearly had surface features, and they were visible, and they moved across the solar disk over the course of days and weeks as the sun slowly rotated. The heavens were not perfect. They were not unchanging. They were, in the most important sense, physical, real, material, subject to the same processes of variation and change as everything below the moon. Galileo published his sunspot observations in 1613 in a book called Letters on Sunspots, written in Italian in the form of correspondence with a Bavarian nobleman. In this book, he engaged in a detailed polemic against a Jesuit astronomer who had suggested the sunspots were small planets close to the sun's surface, rather than markings on the sun itself. Galileo's argument, based on careful measurement of how the sunspots changed shape as they moved toward the edge of the visible solar disk, was that they were on or extremely close to the solar surface, and that their changing apparent shape was exactly what you would expect if flat or slightly raised markings on a rotating sphere were being seen at increasingly oblique angles as they moved toward the limb. This was correct. The sunspots are indeed solar phenomena, magnetic regions where the temperature is slightly lower than the surrounding surface. More importantly for Galileo's broader argument, their existence proved beyond reasonable doubt that the sun was a physical body that changed over time, not a perfect and eternal celestial sphere. Aristotle's two-tier universe, with its fundamental distinction between the imperfect sublunary realm and the perfect celestial realm, was crumbling under the weight of evidence accumulated by a man with a telescope on a rooftop in northern Italy. For several years after his move to Florence, Galileo occupied an unusual and somewhat precarious position. He was a celebrity, the most famous natural philosopher in Europe, fated on his visit to Rome in 1611 with banquets and speeches and the enormous honor of membership in the Accademia dei Lincei, the Academy of the Lynxes, one of the first genuine scientific societies in history. He was privately convinced that Copernicus was right and that his own discoveries confirmed it. And yet he was also living and working in a context where the Catholic Church wielded enormous authority over intellectual life, and where the Copernican system had not yet been formally condemned but was increasingly viewed by conservative theologians with suspicion and alarm. The tension began to surface through a network of controversy and correspondence. In 1611 and 1612, Galileo entered a public dispute with a Jesuit mathematician named Christoph Scheiner over the nature of sunspots. Scheiner, operating under a Jesuit pseudonym to protect himself in case he was wrong, published observations of sunspots and suggested they were small planets orbiting close to the Sun, rather than actual features of the solar surface. Galileo, whose own observations were more extensive and careful, argued that the sunspots were on or very near the Sun's surface and that they moved in a way consistent with the Sun's own rotation. More importantly, he argued that their existence proved the heavens were not perfect and unchanging in the Aristotelian sense. This dispute generated real animosity on Scheiner's part and made Galileo enemies within the Jesuit order at a time when he most needed friends there. In 1612, Galileo published a book on floating bodies, entering into a long-running dispute with Aristotelian professors about why ice floated and what this implied about the density of water. He won the argument convincingly, but the argument itself illustrated the pattern that was becoming characteristic of his career: brilliantly right on the scientific substance, winning on the merits, but generating enemies who would one day find opportunities to strike back. In 1613, Galileo published his Letters on Sunspots, in which he publicly argued for the heliocentric system for the first time in print, if not with complete explicitness. The book caused a stir. And in 1613, another incident occurred that would reverberate for decades. Galileo had a student, a Benedictine monk named Benedetto Castelli, who had been appointed professor of mathematics at Pisa. In December 1613, Castelli attended a court breakfast where the question of Copernicanism and its compatibility with Scripture came up. Castelli wrote to Galileo describing the conversation. Galileo wrote back a long and carefully argued letter explaining his thinking about how Scripture should be interpreted in relation to natural science. The letter, now known as the Letter to Castelli, was an eloquent and theologically sophisticated argument that drew on the Church Father Augustine and other respected authorities. Galileo argued that Scripture was not intended to be a scientific textbook. Its language had been accommodated to the understanding of its original audience of ordinary people who needed guidance toward salvation, not toward astronomy. When the Bible said the sun rose and set, it was using everyday language, not making a precise cosmological claim. God had given humanity two books, the book of Scripture and the book of nature. Both were authored by the same divine intelligence, but they served different purposes, and conflicts between them arose only from misinterpretation of one or both. Galileo even quoted Cardinal Baronio, an earlier Catholic historian who had quipped that the Holy Spirit intended to teach us how to go to heaven, not how the heavens go. It was a witty and theologically coherent argument. The tragedy was that it came at exactly the wrong historical moment, when the Counter-Reformation had made the Church acutely sensitive about anyone other than official theologians interpreting Scripture. The argument Galileo made in the letter to Castelli was not, in itself, theologically radical. The principle he was invoking, that Scripture was not intended to teach natural science and should not be read as a scientific authority, had precedent in Augustine and other Church Fathers. But in the charged atmosphere of the Counter-Reformation, with the Council of Trent having recently asserted the Church's exclusive authority to interpret Scripture, the letter was controversial. Copies circulated. It reached hostile eyes. A Dominican friar named Niccolò Lorini sent a copy to the Roman Inquisition with a complaint. Another Dominican, Tommaso Caccini, preached a sermon in Florence attacking Galileo and Copernicanism. The machinery of ecclesiastical investigation began to turn. Galileo, learning of these attacks, decided to go to Rome to defend himself and to argue against any formal condemnation of Copernicanism. He arrived in December 1615 and spent several months lobbying, arguing, and meeting with church officials. He was received politely, even warmly in some cases. He had friends and admirers in Rome, including Cardinal Maffeo Barberini, a cultivated and intellectually sophisticated Florentine who genuinely admired Galileo's work. But the climate was not favorable. The Inquisition had commissioned a report on the propositions at the heart of the controversy: the immobility of the sun and the mobility of the earth. On February 24, 1616, a panel of theologians delivered their verdict. Both propositions were declared to be philosophically absurd and theologically false, the first one formally heretical and the second at least erroneous in matters of faith. 2 days later, on February 26, 1616, Galileo was summoned to the residence of Cardinal Robert Bellarmine. Bellarmine was the most eminent theologian in the Catholic world, a man of tremendous learning, intellectual honesty, and genuine respect for Galileo's scientific achievements. He also had a clear sense of what the Church could and could not permit at that moment in history. The meeting at Bellarmine's residence was private. According to most historical accounts, Bellarmine told Galileo that the Copernican system had been declared false and contrary to Scripture, and that Galileo must abandon it, must neither hold nor defend it. What exactly happened in that room has been debated ever since. There exists in the Vatican archives a document that records what is alleged to have occurred, an official Inquisition injunction ordering Galileo not only to not hold or defend Copernicanism but not to teach it or discuss it in any way whatsoever. Whether this document accurately reflects what was said and done, or whether it was an unauthorized intervention by a subordinate official, or whether it was even inserted into the file later to strengthen the case against Galileo at his 1633 trial, remains a subject of scholarly controversy. What is not in dispute is that after the meeting, Galileo obtained from Bellarmine a written certificate, signed by the cardinal himself, stating that he had been informed of the declaration that the Copernican doctrine was contrary to Scripture and should not be held or defended. The certificate made no mention of any stronger injunction. This certificate would become critically important 17 years later. On March 5, 1616, the Congregation of the Index published a decree suspending Copernicus's De Revolutionibus until it could be corrected to present the heliocentric system as a mathematical hypothesis rather than physical reality. A book by a Carmelite friar named Foscarini, who had argued that heliocentrism was compatible with Scripture, was condemned outright. Galileo's own works were not mentioned in the decree, but the message was clear. He was being told to stop. Galileo accepted this. He returned to Florence and went quiet for several years, at least publicly. He continued his research, wrote privately, maintained an enormous correspondence with scientists across Europe. He wrote a significant work called the Essai Illinois Saggiator in 1623, an extended argument about the proper method of scientific investigation, written in the form of a polemic against a Jesuit mathematician who had published claims about comets that Galileo considered both wrong and methodologically confused. The Essai was a brilliant and entertaining piece of writing, full of pointed wit, and it included one of the most famous passages in the history of science. Philosophy is written in this grand book, the universe, which stands continually open to our gaze. But the book cannot be understood unless one first learns to comprehend the language in which it is composed. It is written in the language of mathematics, and its characters are triangles, circles, and other geometric figures without which it is humanly impossible to understand a single word of it. And then, in 1623, something happened that seemed to change everything in Galileo's favor. His old admirer Cardinal Maffeo Barberini was elected pope. He took the name Urban VIII. Galileo rejoiced and acted quickly. He dedicated the Essai to the new pope. Urban received it warmly, reportedly so delighted with the book that he had it read aloud to him at table during meals, laughing at Galileo's sharp demolition of his opponents. The contrast between this moment and what would come 9 years later could not be more dramatic. The same man who laughed over the Essai at dinner in 1623 would in 1633 insist, with fury and personal grievance, that Galileo be subjected to the full machinery of the Inquisition. The friendship between Galileo and Urban VIII was one of the great wasted opportunities in the history of the relationship between science and religion, a chance for the Church to integrate the new science gracefully and honestly, squandered by a combination of political pressure, personal vanity, and the impossible tension between an old cosmological system and the new world that a telescope had revealed. The election of Maffeo Barberini as Pope Urban VIII in 1623 must have felt, to Galileo, like a sign that the tide was turning. Barberini had been his friend and correspondent for years. As a cardinal, he had opposed the 1616 condemnation of Galileo. He was a man of culture and intelligence who had written a Latin ode praising Galileo's astronomical discoveries. When Galileo traveled to Rome in 1624 and was received in a series of warm audiences by the new pope, Urban reportedly told him that the Church had not condemned Copernicanism as heretical, only as rash, and suggested that it would be possible to write about the Copernican system as a mathematical hypothesis, a useful calculating tool, so long as it was not presented as physical reality. Galileo took this as permission. He returned to Florence with the explicit goal of writing the major work he had been building toward for years, a systematic comparison of the Ptolemaic and Copernican systems, presenting all the arguments on both sides, allowing the reader to assess the evidence. He worked on it for the better part of 6 years, interrupted by illness, by political disruptions in Tuscany, and by the laborious process of obtaining ecclesiastical permission to publish. The manuscript was completed around 1630 and submitted to the papal censor in Rome. The book was structured as a dialogue, a literary form with ancient roots in Plato, and Galileo used it brilliantly. 3 characters met over the course of 4 days and debated the 2 great cosmological systems. Salviati was the Copernican, clearly the author's own mouthpiece, a man of refined intelligence who presented the heliocentric case with mounting eloquence and skill. Sagredo was the educated layman, open-minded and curious, who gradually came to see the justice of the Copernican arguments. And Simplicio was the defender of Aristotle and Ptolemy, a traditionalist who wielded the stock arguments of the old cosmology and who, over the course of the 4 days, found each of his positions systematically dismantled. The name Simplicio was, on one level, simply the name of a 6th-century commentator on Aristotle. But in Italian, the word simplice also carries the meaning of simpleton, and it was impossible not to notice that the character who represented the Aristotelian and church position was, by the end of the dialogue, a figure of ridicule. Simplicio's arguments were defeated, his positions shown to be logically incoherent, his confidence deflated. And in the crucial final pages of the book, Pope Urban's personal theological argument, which Urban had specifically asked Galileo to include, was given to Simplicio to deliver. The argument held that since God is omnipotent and can create the world in any way he pleases, no scientific observation can prove which cosmological system is actually correct. We must bow to divine authority. It was an argument Urban was proud of. It was also an argument that, coming from Simplicio's foolish mouth, sounded like exactly what it was: a retreat into incapable authority when the empirical arguments had been lost. Whether Galileo intended this as a personal insult to Urban is a matter of dispute. Most historians believe he did not, that he was simply unable to think of any other character to give the Pope's argument to. Others think he was blinded by the confidence of a man who had spent his entire life being the smartest person in any room, who genuinely believed that Urban, being intelligent, would recognize the force of the scientific arguments and accept them, and who misjudged how seriously Urban would take the representation of his own thinking in the mouth of a fool. Whatever the psychological truth, the result was catastrophic. The book was published in Florence in February 1632, with formal permission from both the Roman and Florentine censors. It was written in Italian rather than Latin, which made it accessible to any educated reader, not just scholars. It had a formal preface, added at the insistence of the censors, presenting the work as a hypothetical exercise. But the arguments within it were so compelling, so carefully crafted, and so clearly favorable to Copernicus that the preface fooled no one. The book was the most powerful scientific argument for heliocentrism that had ever been published, and it was written by the most famous scientist in Europe. The first sign of trouble came in July 1632 when Urban VIII had the dialogue removed from bookshops. An ambassador's letter from that period describes Urban as having exploded into anger when he finally understood what Galileo had done. The Pope felt deceived, and perhaps he was, though probably not by deliberate malice. He had been maneuvered into appearing to endorse a book that made his theological arguments look foolish. His political enemies within the Church, particularly among the Spanish faction of cardinals who had been trying to expose him as too tolerant of heresy, were delighted to see him compromised. Urban had little choice but to act. In October 1632, an Inquisition officer arrived at Galileo's house in Florence with a summons to appear before the Holy Office in Rome. Galileo was 68 years old, in fragile health, suffering from a hernia and from what modern physicians think was probably advanced glaucoma. He begged to have the proceedings moved to Florence. He sought medical certificates attesting to his ill health. The Grand Duke of Tuscany tried to intercede on his behalf. All appeals were denied. Pope Urban insisted that Galileo make the journey to Rome in person and in winter. On February 13, 1633, after a 23-day journey by litter, Galileo arrived in Rome. He was lodged not in prison but in the comfortable apartments of the Tuscan ambassador, a sign of the unusual leniency being extended to him in deference to his age and fame. And then the waiting began. The proceedings against Galileo before the Roman Inquisition took place across 4 main sessions during the spring of 1633. The lead inquisitor was Vincenzo Maculani, Commissary General of the Holy Office. The charges were, in Athens, that Galileo had violated the injunction of 1616 by publishing a book that defended the Copernican system as physically true. The critical piece of evidence on which the prosecution's case rested was the document in the Inquisition's file purporting to record the injunction of February 26, 1616. the one that forbade Galileo not merely to hold or defend Copernicanism, but to teach or discuss it in any matter whatsoever. Consider the human situation for a moment. Galileo was 68 years old. He was not well. The journey from Florence had exhausted him. He was living, courtesy of the Grand Duke's ambassador, in relative comfort compared to most Inquisition defendants, but he was nonetheless a man who knew his life's work was on trial. He had spent 30 years studying the heavens, filling notebooks with careful observations, writing books that represented the deepest intellectual labor of his life, and now he sat before a panel of men who had already decided what was true and what was permitted, and who had the power to imprison him or worse. He had few real defenders left in Rome. His old friend Cardinal Francesco Barberini, the Pope's nephew, was trying quietly to secure lenient treatment, but the Pope's fury had made the political atmosphere toxic. The first interrogation took place on April 12. Galileo was asked whether he knew why he had been summoned. He responded that he imagined it was because of his recently printed book. He was asked about the 1616 meeting with Bellarmine and about the nature of the instruction he had received. He produced the certificate Bellarmine had given him, which said only that he had been told not to hold or defend the Copernican opinion, with no mention of the stronger prohibition against teaching or discussing it. This document was Galileo's strongest card. If the only injunction he had received was not to hold or defend Copernicanism, and if his book was a balanced presentation of both sides rather than an advocacy piece, then perhaps he had not violated any prohibition at all. Galileo then made a claim that most historians find difficult to credit but that he maintained throughout the proceedings, that the dialogue, properly read, was not an advocacy for Copernicanism but actually a refutation of it, that he had presented the arguments of the Copernican side only to show their weaknesses, and that the book therefore did not violate his commitment. He even suggested that if he were permitted to revise the book, he could add further arguments on the Ptolemaic side to make it clearer that the geocentric position was the stronger one. No one believed this. 3 theologians commissioned to examine the dialogue reported back on April 17 with the conclusion that the book unambiguously favored and defended the Copernican system. The evidence was overwhelming, and from the Inquisition's perspective, the book's obvious preference for Copernicus was exactly what made it so dangerous. A book that simply discussed the Copernican system as one theoretical option among several would have been manageable. A book that systematically demolished the Ptolemaic arguments and left Copernicus standing as the obvious victor was something else entirely. Anyone who read the dialogue could see this. In the days after its publication in 1632, educated readers across Italy had seen it immediately. The pretense that the book was impartial was one that satisfied no one, and Galileo's insistence on maintaining it at his trial must have struck the inquisitors as either an insult to their intelligence or a sign of how badly frightened he was. In late April, the Inquisition's Commissary General paid a private visit to Galileo and proposed an arrangement. Cardinal Francesco Barberini had been working to find a compromise that might spare Galileo the full force of the sentence. If Galileo were to admit that the book had gone too far in presenting the Copernican arguments too favorably, perhaps unintentionally, the inquisitors might be able to recommend a lenient sentence. Galileo agreed. On April 30th, in his second formal appearance before the Inquisition, he admitted that reading back through the dialogue he could see that a reader might conclude that the Copernican side had been presented with more force than the Ptolemaic side. He attributed this to his own vanity, his desire to appear clever and eloquent, rather than to any actual conviction that heliocentrism was true. He denied still that he believed the earth moved. His defense was essentially that he was a better rhetorician than he was a reasoner, and that he had dazzled himself with his own arguments. It was a humiliating thing to claim, and Galileo knew it. He was a proud man. This was not the kind of statement he had ever previously been willing to make about himself. But the alternative was worse. This partial admission was not enough for Urban VIII. The Pope wanted a full public spectacle. He wanted a formal sentence, a tough examination, public abjuration, and imprisonment. His anger had not dissipated. If anything, his political situation within the Church had made him less inclined to show mercy to someone who had so completely embarrassed him. A third session of questioning, on May 10th, produced nothing new of substance. Galileo maintained his position. The proceedings moved toward their conclusion, which everyone in Rome already knew. On June 22, 1633, in the great hall of the convent of Santa Maria sopra Minerva in Rome, the final act was played out. Galileo was brought before the assembled cardinal inquisitors. He knelt. He was dressed in the white shirt of penitence, the garment worn by those condemned of spiritual error. 7 of the 10 cardinal inquisitors were present to sign the sentence. 3, including Cardinal Francesco Barberini, declined. The sentence was read aloud. He had been found vehemently suspect of heresy, of having held and believed a doctrine declared false and contrary to Holy Scripture, namely that the sun is the center of the world and immovable, and that the earth is not at the center and moves. He was required to abjure, curse, and detest these opinions. He was sentenced to formal imprisonment at the pleasure of the Inquisition. His dialogue was banned. And in an action not announced publicly in the courtroom, the publication of any of his current or future works was also forbidden. An extraordinary measure that extended even to works he had not yet written and that demonstrated how deeply the Church wanted to silence this particular voice. The hall was quiet. Outside, Rome went about its business in the June heat. Somewhere in the city, musicians were playing. Children were running in the courtyards. The Tiber was moving toward the sea. And in this solemn hall, an old man was kneeling on the stone floor with his hands on the Holy Gospels. Then Galileo read his abjuration. In a clear voice, or as clear as an old man in his condition could manage, he declared, "I, Galileo Galilei, son of the late Vincenzo Galilei of Florence, aged 70 years, arraigned personally before this tribunal and kneeling before you, most eminent and reverend Lord Cardinals Inquisitors General against heretical depravity throughout the whole Christian commonwealth, having before my eyes and touching with my hands the Holy Gospels, swear that I have always believed, do believe, and by God's help will in future believe, all that is held, preached, and taught by the Holy Catholic and Apostolic Roman Church." He then specifically abjured the opinion that the sun is the center of the world and immovable, and that the earth is not the center and moves. He abjured, cursed, and detested these errors and heresies. He promised to denounce any other heretic he knew of, and he signed his name. "I, Galileo Galilei, have abjured as above with my own hand." The legend that Galileo, rising from his knees after this recantation, muttered under his breath, "Aper esse move," and yet it moves, is one of the most famous stories in the history of science. It is almost certainly not true in the form it has come down to us. The phrase first appears in a painting that may date from the 1640s, within a year or two of Galileo's death, but the story of him saying it in the trial hall comes from sources that are more than a century later. If Galileo, in the summer of 1633, had openly muttered any defiance of his abjuration in the presence of the Inquisition, the consequences would have been immediate and severe. He would not have been forgiven. The story is a legend, perhaps a legend born from what people believed was in his heart, but a legend nonetheless. What people wanted to believe was true was that science could not be permanently silenced, that the truth would speak through any mouth that had been forced to deny it. That belief was not wrong. It just was not the mechanism through which the truth of the Earth's motion was eventually vindicated. What is certainly true is that only 7 of the 10 cardinal inquisitors signed the sentence. 3 declined, including Cardinal Francesco Barberini. Their reasons are not recorded, but their dissent from the majority verdict was a quiet act of conscience in an institution that was not known for tolerating dissent. And what is also true is that on the very next day, June 23rd, the formal sentence of imprisonment was commuted to house arrest. Galileo was transferred to the custody of the Florentine ambassador, and from there, after several days, to the custody of the Archbishop of Siena, his old friend Ascanio Piccolomini, who received him with warmth and care and helped him begin the long process of recovering from the psychological devastation of the previous months. In Siena, housed in the Archbishop's palace, waited upon with genuine affection, Galileo slowly returned to something approaching equanimity. He began to think again. He began tentatively to work. In December 1633, Galileo was granted permission by the Pope to return to his own home, the Villa Il Gioiello, a small farmhouse in Arcetri, a hillside village just south of Florence, a few hundred meters from the convent where his daughters lived. He was to remain there under house arrest, forbidden to travel, forbidden to publish, forbidden to receive visitors without the permission of the local inquisitor. He was 69 years old. He would never leave the vicinity of Florence again. The Villa Il Gioiello, the Jewel, was a modest 2-story stone farmhouse set among the cypresses and olive groves of the Arcetri hills. From its upper windows, on a clear day, Florence spread out below. The dome of the cathedral, the tower of the Palazzo della Signoria, the ribbon of the Arno, the whole panorama of the city where Galileo had grown up and to which he had returned in triumph after his Padua years. Now he returned to it as a prisoner, allowed to see but not to be seen, allowed to think but not to speak. The first months at Arcetri were shaped by grief. His older daughter Virginia, Suor Maria Celeste, had been his most constant and devoted companion through the years of his troubles. She had managed his correspondence, had interceded with the convent authorities to help him in practical matters, had written him hundreds of warm and loving letters that constitute one of the most remarkable records of father-daughter relationship in literary history. When Galileo had been ordered to read the 7 penitential psalms once a week as a condition of his sentence, Maria Celeste had obtained permission to take this obligation on herself, to spare her father. She was barely in her 30s when Galileo returned to Arcetri, worn down by the poverty and physical harshness of convent life. The nuns of San Mateo were poor clares, vowed to absolute poverty, and their daily existence was genuinely hard. Inadequate food, cold stone cells, few resources for illness or comfort. Maria Celeste's letters to her father were filled with requests for practical help alongside her expressions of love. Medicines, food, cloth, small sums of money. She asked him for everything a daughter could reasonably ask a father and more, because she had no one else. On April 2, 1634, just months after Galileo's return to Arcetri, Suor Maria Celeste died. She was buried in the convent church, scarcely a kilometer from the farmhouse where her father sat in his house arrest. Galileo, from his hilltop, could not even attend her burial with anything like proper ceremony, given the terms of his confinement. His grief at her death was immense and lasting. He wrote to his friend Elia Diodati in Paris that he felt a hernia, heart palpitations, great sadness and melancholy, loss of appetite, and hateful sleeplessness. The personal darkness was deepening at the same rate as the physical darkness in his eyes. He recovered by working. It was the only thing he knew how to do when the world was against him, and he did it now with a kind of furious determination that belied his age and his circumstances. Under house arrest, forbidden to publish, forbidden to receive many visitors, Galileo worked on the physics project he had been building for 50 years. The inclined plane results from Padua, the pendulum observations from Pisa, the analysis of projectile motion, the theory of uniform acceleration, the mathematics of the strength of materials. All of this, the physics rather than the astronomy, the science that no inquisitor could easily call heretical, because it was about balls rolling down slopes rather than planets orbiting the sun, Galileo began systematically writing up as a comprehensive treatise. The book he was writing was titled Discorsi e dimostrazioni matematiche intorno a due nuove scienze, Discourses and Mathematical Demonstrations Relating to Two New Sciences. The two new sciences of the title were the science of the strength of materials and the science of motion and mechanics, what we would now call strength of materials engineering and kinematics. The structural problem that opens the book is elegant and immediately engaging. Why can you not simply scale up a small structure to make a larger one? Why does a large bone have to be proportionally thicker than a small one to support the same relative weight? Why does a mouse survive a fall from a height that would kill a man? The answers lie in how the strength of materials scales with dimensions, and Galileo worked through the mathematics with the precision of a man who had been thinking about these questions for decades, surrounded by the arsenal of Venice, watching craftsmen build ships and handle enormous weights. The second and greater science was the science of motion. Here Galileo's 50 years of thinking came to their full flowering. He laid out the law of uniform acceleration with the rigor of a mathematical proof and the backing of 50 years of experimental testing. A body falling under gravity accelerates at a constant rate, gaining equal increments of speed in equal intervals of time, and the total distance it covers in any given time is proportional to the square of that time. He showed how this principle, derived from the inclined plane, applied identically to freely falling bodies. He worked out projectile motion in its complete mathematical form. A ball launched horizontally follows a parabolic path because its horizontal motion is uniform while its vertical motion is uniformly accelerated. Tables of range and height for projectiles launched at different angles followed directly from this analysis, with a mathematical precision that had never been applied to military ballistics. He returned to pendulums, confirming that their period depends on length alone, not on the weight of the bob or the width of the swing. These things together constituted a new physics, a physics of measurable, predictable, mathematically expressible motion, and they rendered the Aristotelian account of natural movement as obsolete as a candle in a room where someone had just turned on an electric light. The book was written in the same dialogue form as his earlier dialogue, with Salviati, Segreto, and Simplicio as the interlocutors. But this time Simplicio was less of a figure of fun and more of a representative of Galileo's own earlier thinking, his younger scientific self asking the questions that the mature Galileo could now answer. The writing proceeded through 1635, 1636, 1637. In 1638, Galileo went completely blind. The progressive deterioration of his vision had been ongoing for years, probably the result of advanced glaucoma combined with the effects of staring at the sun through inadequate filters during his sunspot observations decades earlier. By early 1638, he could no longer see anything at all. He described the experience in a letter with a restrained grief more moving for its understatement. This universe which I, with my astonishing observations and clear demonstrations, had enlarged 100,000 times beyond the belief of the wise men of bygone ages, henceforward for me is shrunk into such a small space as is filled by my own bodily sensations. A poet might imagine this as a terrible irony. The man who had shown humanity new worlds with his telescope, unable to see the world around him in his final years. Galileo himself did not dwell on the irony. He was still thinking. He was still working. He dictated. He had visitors read to him. He had pupils take dictation and carry his mathematical arguments forward on paper that his own hands could no longer hold. The Discorso was smuggled out of Italy by a trusted intermediary, the French ambassador François de Noailles, who had been a student of Galileo's years before. It could not be published in Italy or anywhere under Roman Inquisition jurisdiction, but in Holland, in the Protestant Dutch Republic, the Elsevier printing house in Leiden operated outside papal authority. The manuscript reached Leiden through a chain of trusted correspondence, and in 1638 the book was published. Galileo received his own copies that year, holding them with hands that could no longer see the pages he was touching. He knew what was in them. He had written every line. The Two New Sciences, as it has come to be known, was immediately recognized by those who read it as a work of the first importance. It placed the mathematical description of motion, the law of uniform acceleration, the parabolic trajectory of projectiles, and the principles of the strength of materials on rigorous foundations that went far beyond anything that had previously been published. Albert Einstein, 3 centuries later, praised it as one of the most important works in the history of physics. The physicist and science historian Stillman Drake called it the foundation stone of modern mechanics. In the summer of 1638, the English poet John Milton visited Galileo at Arcetri. Milton was on a grand tour of Europe, absorbing the intellectual culture of the continent before the political upheaval that would soon engulf England. What exactly passed between the poet and the blind old scientist we do not know. No detailed account of the conversation survives. We know only that it happened and that it mattered to Milton. He mentioned the visit years later in his great defense of freedom of the press, the Areopagitica, describing Galileo as the great and famous Galileo, grown old, a prisoner to the Inquisition for thinking in astronomy otherwise than the Franciscan and Dominican licensers thought. The image of the old, blind, imprisoned sage became one of the defining images of Galileo's legend. Milton himself would go completely blind in 1652, and his great epic poem Paradise Lost, composed through dictation in the darkness of his own middle age, contains passages of cosmic description, views of the solar system, discussions of the planets and the stars, that bear the unmistakable imprint of what he had absorbed from that visit to Arcetri. In a real sense, Milton carried Galileo's cosmological vision into one of the supreme works of English literature. Galileo's health continued to decline. He suffered from a painful hernia that made movement difficult. He was permitted, on grounds of health, to travel occasionally to Florence to see physicians. He continued to receive pupils and visitors who would take away his ideas and disseminate them through the scientific networks of Europe. He continued to correspond with scientists throughout the continent, dictating his letters and having their replies read to him. Among the visitors who came to Arcetri in Galileo's final months was a young Florentine mathematician named Evangelista Torricelli, who arrived in October 1641 and remained as Galileo's companion and assistant for the last 3 months of his life. Torricelli absorbed everything that Galileo had not yet written down, and he went on to invent the barometer and to make fundamental contributions to fluid mechanics. The problem of why suction pumps cannot lift water beyond a certain height, roughly 34 feet, a puzzle that Galileo had noted but never fully explained, was solved by Torricelli using the principles Galileo had established. The weight of the atmosphere presses down on the water's surface, and the pump can lift the water only as high as the atmospheric pressure can support a column of water. Measure this in the denser liquid mercury and you get a column of about 30 inches, which is exactly the height of a standard barometer. Science continued. Even in the last months of the master's life, it continued. Pope Urban VIII refused to allow Galileo to be buried with honors in the Basilica of Santa Croce in Florence, the great church where the most distinguished Florentines were typically interred. Urban had not forgiven him. Galileo was buried quietly in a small room adjoining the novice chapel of the basilica. It was not until 1737, nearly a century later, that his remains were moved to the main body of the basilica, where a marble monument was erected and where he rests today, near Michelangelo's tomb, honored at last by the city that had sometimes supported and sometimes abandoned him. Isaac Newton was born on January 4, 1643, by the Gregorian calendar, or January 4, 1643 New Style, which would have been December 25, 1642 by the old Julian calendar still used in England at the time. The dates are close enough to sustain the poetic resonance that has attached itself to the story ever since. The year Galileo died was the year Newton was born. The chain of discovery was unbroken. The relay baton passed through the darkness. To assess Galileo's legacy is to attempt to measure the influence of a man who changed, in fundamental ways, not just what we knew about the world but how we go about the business of finding things out. This is a harder thing to measure than a discovery or an invention, because the scientific method is not a piece of technology or a fact about a planet. It is a way of thinking, a set of habits of mind, a systematic discipline for separating what is true from what merely seems true or is comforting to believe. And Galileo, more than any single figure before Isaac Newton, embodied and articulated this approach. Consider what the scientific method, as Galileo practiced and developed it, actually consists of. It begins with careful, systematic observation of natural phenomena. Galileo observed pendulums swinging, balls rolling down inclined planes, stars near Jupiter shifting their positions over successive nights, the phases of Venus, the shadows of mountains on the moon. He did not begin with a theory and fit the facts to it. He began with the facts and built toward a theory. This seems obvious now because Galileo and those who followed him made it obvious. Before Galileo, it was far from obvious. The standard approach in natural philosophy was to start with the text of Aristotle and argue toward the world. Galileo reversed this. He started with the world and argued toward the truth. But observation alone is not enough. The second crucial element of Galileo's method was quantification. He insisted that natural phenomena be described in the language of mathematics. Not things fall at different rates depending on how heavy they are, a qualitative claim that could mean anything, but the distance a falling body covers is proportional to the square of the time elapsed, a precise, mathematical, testable claim. This insistence on mathematical precision was what allowed Galileo's results to be reproduced, checked, and extended by others. It was what allowed his claims about the behavior of falling bodies and projectiles to eventually be incorporated into Newton's laws of motion. A mathematical description of nature is a description that can be right or wrong in a clear, measurable sense. A qualitative description can always be adjusted to accommodate any result. Galileo understood this, and he made the insistence on mathematical precision a fundamental principle of scientific inquiry. The third element was experiment as a tool of discovery, not just illustration. Galileo did not conduct his inclined plane experiments to demonstrate a theory he already held. He conducted them to find out what actually happened. The water clock, the careful measurements, the repeated trials at different angles and with different masses, all of these were directed at a genuine question. What is the actual mathematical relationship between the time elapsed and the distance traveled? The experiments were designed to answer this question, and they did. This use of systematic, controlled experiment as a primary source of knowledge about the physical world was one of Galileo's most lasting contributions. The fourth element, perhaps the most famous in the history and philosophy of science, is what Galileo articulated when he wrote that the book of nature is written in the language of mathematics. Nature, Galileo asserted, is mathematically structured. The regularities we observe are not accidents. They are the expressions of precise mathematical relationships that exist in nature independently of human observation. The task of the scientist is to discover these relationships through observation and experiment, to read the book of nature as it is actually written, not as previous human authorities have interpreted it. This vision of nature as a mathematical structure, knowable through systematic empirical investigation, has been the driving idea of physical science from Galileo's day to our own. The immediate scientific inheritors of Galileo's work were numerous and distinguished. Johannes Kepler, his contemporary, had already worked out the three mathematical laws describing planetary motion. The orbits are ellipses, the radius vector sweeps equal areas in equal times, and the orbital periods are related to the distances from the Sun by a precise mathematical law. Galileo and Kepler were two different kinds of scientific genius, the one empirical and experimental and suspicious of abstract theorizing, the other mathematical and mystical and drawn to patterns in the data, but they were moving in the same direction. Between them, they had described the mechanics of the solar system with a precision that no previous generation of astronomers had approached. Isaac Newton read Galileo with deep attention. Newton's first law of motion, the principle of inertia. A body in motion stays in motion, a body at rest stays at rest, unless acted upon by an external force, owes an enormous debt to Galileo's recognition that uniform motion in a straight line requires no explanation. It is change in motion that requires a cause, and the measure of that cause is what Newton would call force. Newton's second law, relating force, mass, and acceleration with the precise formula that force equals mass multiplied by acceleration, built directly on Galileo's quantitative analysis of uniform acceleration in falling bodies and on inclined planes. Newton's third law, that every action has an equal and opposite reaction, completed the architecture of classical mechanics. Newton's synthesis, the Principia Mathematica, published in 1687, 45 years after Galileo's death, unified the physics of motion on Earth with the physics of motion in the heavens, showing that the same laws that govern Galileo's rolling balls and falling cannonballs also govern Kepler's orbiting planets and the Moon's monthly circuit of the Earth. The law of universal gravitation, which accounted for why the Moon stayed in orbit rather than flying off into space, used the very numerical relationship between distance and gravitational force that Galileo's inclined plane experiments had helped establish. When Newton famously said, in a letter to Robert Hooke in 1676, that if he had seen further than others it was by standing on the shoulders of giants, the acknowledgement was genuine. Galileo was one of those giants. It was the most complete vindication any scientist could have wished for, and it came from the greatest scientist of the following generation. Albert Einstein, 2.5 centuries later, reflected on Galileo's legacy in a preface he contributed to a modern edition of the Dialogue. He wrote that what Galileo represented was the passionate fight against any kind of dogma based on authority, the insistence that only experience and careful reflection are accepted as criteria of truth. Einstein recognized in Galileo a kindred spirit, a man who was willing to follow the evidence wherever it led, regardless of what the authorities said, regardless of personal consequence. Einstein himself had done something intellectually similar in 1905, when he proposed the special theory of relativity against the resistance of the established physics community, discarding cherished assumptions about space and time because the experimental evidence demanded it. The Galilean spirit was alive in him. The Catholic Church, for its part, moved slowly but eventually toward a full accounting of what had happened in 1633. The ban on heliocentric books was effectively lifted in 1758, when Pope Benedict XIV had the general prohibition removed from the index of forbidden books. Copernicus's own book and Galileo's Dialogue remained on the index until 1835, when they were removed entirely. This was a process that took 2 centuries, not 2 years. An institution as old and as large as the Catholic Church does not change its positions lightly, and the humiliation of admitting that the Inquisition had condemned a man for stating a truth is not a small thing to accept. In 1979, Pope John Paul II called for a thorough re-examination of the Galileo affair by an interdisciplinary commission of scholars. In 1992, 13 years after that call, the Pontifical Academy of Sciences formally concluded the process. The Pope, speaking to the Academy on October 31, 1992, acknowledged that the theologians of the Inquisition had made an error. They had failed to distinguish between the claims of empirical science and the claims of biblical revelation. They had treated a question of physical fact as though it were a question of theological authority, and they had been wrong. The Pope noted specifically that Galileo had shown better theological judgment than the theologians who condemned him, because Galileo had understood correctly that the Bible was not a scientific textbook and that the language of Scripture, when it described physical things, should not be taken literally. The apology came 359 years after the trial. It was incomplete in the eyes of many historians, and it was careful not to admit that the condemnation had been a formal doctrinal error rather than a merely prudential misjudgment. But it was real. The man who had been buried in a side chapel, denied the honors of the main basilica, had been vindicated by the institution that had silenced him. He had needed no vindication from history. History had been on his side since the day Newton published the Principia. But the symbolic weight of the Church's acknowledgement carried its own meaning. In 1989, NASA launched the Galileo spacecraft, an unmanned probe intended to study Jupiter and its moons. It arrived at Jupiter in 1995 and spent 8 years orbiting the planet, transmitting back the most detailed images and measurements of Jupiter and the Galilean moons ever obtained. The probe found evidence for subsurface liquid water oceans on Europa, one of the 4 moons Galileo had discovered with his Handware telescope in January 1610. Europa's ocean may be the most likely place in our solar system, outside the Earth, to harbor life. The man who first saw those 4 points of light shifting around Jupiter from his balcony in Padua could not have dreamed that one day a machine bearing his name would orbit those distant moons and find hints of possible life beneath their icy surfaces. His name is also attached to the unit of acceleration, the gal, used in geophysics to measure gravitational variations. The main space telescope competing with Hubble for observations of our galaxy and beyond is the Euclid mission, launched in 2023, and one of its predecessors, a European satellite for global navigation and positioning, bears the name Galileo as the European alternative to GPS. His image appears on Italian euro coins. The Museo Galileo in Florence houses his original telescopes, his compass, and one of the most remarkable relics in the history of science. A mummified middle finger, the third finger of his right hand, severed from his body during the 1737 exhumation, preserved in a glass globe, and pointing permanently upward in what the museum's curators describe simply as a relic, but which later generations have invested with a gesture that Galileo himself was too careful, or too wise, or too old to actually make in his lifetime. That pointing finger, that gesture, something in it captures the entire arc of his life, the long argument with the universe and with the institutions that tried to tell him what the universe was allowed to be. He was right. He had always known he was right. The earth moves. The sun stands still, or at least relatively still, at least within the local frame of reference we call the solar system. The moons of Jupiter turn in their orbits. The moon is rough and mountainous. The heavens are not perfect. Nature is written in mathematics. And the only way to read what nature has written is to look and measure and reason and keep looking when what you see contradicts what you have been told. Galileo Galilei died in the first week of January 1642, in a small farmhouse on a hill outside Florence, blind and under arrest. He died as he had lived. A scientist, a man of faith, a man of enormous pride and occasional stubborn error, a man who loved music and poetry and argument and the texture of physical things in his hands, a man who had stared into the night sky until the sky gave up its secrets, and who had spent the rest of his life trying to tell the world what he had seen. The world eventually listened. And so we close this chapter of history with the image we began with, a tired old man in a darkened house who can no longer see the stars he spent his life studying. But the stars do not need him to see them in order to be what they are. Jupiter spins. Io and Europa and Ganymede and Callisto, those four little sparks of light that surprised a sleepless mathematician on a January night in 1610, continue in their orbits with the same quiet regularity they have always maintained. The moon still carries the mountains and craters that Galileo sketched by candlelight in the winter of 1609, when the world was still young enough that no human eye had ever seen them. What Galileo gave us was not just a set of facts about the universe. He gave us a way of approaching every fact we have learned since. He showed us that the universe has a language and that we are capable of learning it. He showed us that the authority of tradition is not sufficient justification for belief, that the world must be consulted directly, with open eyes and careful instruments and a willingness to follow the evidence wherever it leads, even when it leads somewhere uncomfortable. He showed us, above all, that the truth is worth the trouble it causes. And if that is a lesson we still need to be reminded of for centuries after his death, then perhaps the best we can do is to remember him, here in the quiet hour between wakefulness and sleep. An old man, a philosopher, a scientist, a father, a prisoner, and a finder of worlds. He is with us still in every laboratory, in every observatory, in every student who picks up an instrument and points it at the unknown and dares to write down what she sees. He is with us in the mathematics we use to describe the arc of a ball thrown through the air, in the laws of motion that Newton built on the foundation Galileo poured, in the physics that eventually gave us the technology to build the Galileo spacecraft and send it all the way to Jupiter, to visit the moons he was the first human being to name. A precise move. And yet it moves, not just the Earth. Everything that was understood to be fixed and final and eternal in Galileo's world has since been moved, revised, turned over, and illuminated from angles no one expected. Because that is what science does. And Galileo, more than almost anyone else who has ever lived, is the reason science does it. He lived. He looked. He wrote it down. The rest, as they say, is history. But not only history. It is also how we understand the sky above us tonight and every night and always. If this story has carried you somewhere new tonight, we'd love for you to carry us forward too. Subscribing to Sleep Story takes just a moment, and it means you'll never miss a new story. Like this video if you'd like to see more journeys through the lives of history's great minds, and leave us a comment below with a figure from history whose story you'd like to hear next. We have many more stories to tell, and we are very glad you are here to hear them. Good night.